Alrighty, here is section 3.7 example 2, and we're going to actually change it up a little bit after we do it the first time. So we'll do it like them first, and then example 2, they have a function, so find the points. I'll put the S in parentheses because you never know for sure if there's more than one. Find the points on y equal, and what the heck is that? It is 4 minus x squared. Closest to the point 0, 2. Okay, so now I'm gonna switch over to Desmos real quickly, and just so we can see this, and I'm gonna write it as f of x equals 4 minus x squared. So there's the picture of our function, and then I'm going to toss in the point here 0, 2, and so we got our point right there. I'm going to get rid of the menu on the side. It gives us a little more room. And there we have it. Okay, so I'm trying to find points on the graph here closest to that point, and with the symmetry, I do assume I'll probably find 2 points. And so let's go back here, and so if so I'll draw kind of what we had. And I'm looking at this distance to some other point, and so the distance between a point x1, y1 and another point x2, y2 is equal to the square root of x1 minus x2 squared plus y1 minus y2 squared. Okay, now they do mention this. I was looking to see if they do talk about this. In the end, so what we want to do is we want to minimize D. But here's the thing, is that it looks like that square root's going to be really nasty to work with because we've got the squares under there. But the square root, let's look at that outside function. So let's take a moment here and just look at the function f of x equals the square root of x. And that function is strictly increasing, right? And so what that means is that as I make the square root of something smaller, I am making that something also smaller. So here's, say, some x1 and some other x2. What's happening, right, is that as I move left and decrease x, I'm decreasing the square root of x. But a different way to look at it is, as I come down, in the square root, as I make the square root smaller, I make x smaller. Okay, and so since the square root is strictly increasing, I can minimize x1 minus x2 squared and y1 minus y2 squared instead of the square root of the expression. Okay, so that's one way to look at it. Another way to look at it is that the x squared function is strictly increasing. So there are a couple ways to decide that we can get rid of that square root. And one way was just that the square root itself is a strictly increasing function, and so if I'm trying to minimize it, I can minimize the square root function by minimizing x. Okay, so that's one way to see it. Another way to see it is that I can look at the function x squared, and it's strictly increasing, and so if I want to minimize x, if I want to make x here as small as possible, I can do that by minimizing x squared. And so another view is minimize d squared instead of d. Okay, and either one gets us to the idea that what we want to minimize is x1 minus x2 squared plus y1 minus y2 squared. And so it just makes our calculation easier. And so we have that, and so with that, I just need to figure out what these x1 and x2 are and so forth. All right, so my points are the point 0, 2, and any point on the parabola. Well, what's a point on the parabola? Well, it's a point x with that y, but how do I get y? 4 minus x squared. So what I can do is I can come in here and say, okay, we're going to let x1, y1 be that point 0, 2, and we'll let x2, y2 be the point x, y, but that is x and 4 minus x squared. So there are our points. So now we want to minimize. And see again, like they did in example 1 and I talked about in example 1, I got all kinds of variables here, x1, x2, y1, y2, and so forth. That's okay, I'll hopefully get rid of them, and if I can't, I guess I'll decide I don't know how to do the problem. But so now I want to minimize the x1 minus x2 squared, so I've got 0 minus x squared plus the, minus in there, y1 or y2 squared, so minus 4x squared. Okay, now I'm going to rewrite that as x squared, and then plus. Now I've got 2 minus 4, which is a negative 2, and a minus x squared. So in here I have x squared minus 2 squared. Alright, so at this point I can either use the chain rule or I can multiply this thing out. I think I'm just going to go ahead and use the chain rule. So this d squared, what should we call it? I don't know, I'll call it big D. How about that? And so I want to find the critical number, so d prime of x, I get 2x plus, now the chain rule, bring down the 2, that's x squared minus 2, and then I need to multiply by the derivative of what's inside, so that's 2x, and I need to set all that equal to 0 to find the critical numbers. Okay, now what I notice is I've got a 2x there and a 2x there, so I'm going to factor that out. I'm not going to write an equal sign there. I have 2x, and then I have 1 plus 2 times x squared minus 2, and that equals 0. So either x equals 0 from the 2x equals 0, or 1 plus 2 times x squared minus 2 is equal to 0. Well, x equals 0 actually is not a bad guess. I mean, if I come back up to this picture, you know, that would be the x equals 0 would be the point right above 0, 2. Now, if we go back here, looking at it, I don't think that's going to be the answer, right? I've got x equals 0, right, you know, that's that one, but if I look here, that looks shorter, definitely. And actually, well, let's see, 1, 2, 3, oh wait, no, those are each 1. So this is 2 units away, but this is less than 2 units away straight sideways. So see, that I think is actually going to be a relative maximum. Okay, but I don't know that for a fact. I mean, it looks like it is. And so let's keep looking at this other side. So I have 2 times x squared minus 2 is equal to negative 1. And so x squared minus 2 is equal to negative 1/2. And add 2 to both sides, I get 3/2. And so x here is plus or minus the square root of 3/2. Okay, so there are my critical numbers, 0 and then plus or minus square root of 3/2. I'm going to check concavity. So I'm going to do d double prime. Now I can just look back at the function. D double prime better be negative everywhere except possibly oh wait, never mind. No, I take that back. Sorry, misspeaking. I got ahead of myself, so sorry. So d double prime of x, I need to take the derivative of all this stuff. So I'll get a 2 and then plus. Now I have 2, 4, I think, you know, here, instead of doing the product rule, okay, let me backtrack a minute And let's rewrite d prime of x as our 2x, and then plus, I have 2 and a 2, that makes 4. And then I'm going to multiply through by the x, so I get x cubed minus 2x. Like that. And I think I'm going to continue to simplify, so I get a 4x cubed, and here's plus 2 minus 8, so that's minus 6x. So now I'll take the second derivative, 12x squared minus 6, and so what I need to do is check the concavity of each of these things. So d double prime of 0, one of the critical numbers, is negative 6, concave down, and that's a maximum, right? A relative maximum. So not what we want. And then d double prime of the square root of 3 halves. Now, that's going to be the same as the negative square root of 3 halves, because I'm just squaring the number I put in. So this is 12 times 3 halves minus 6. And that's 18 minus 6, or 12. So this one, and so d double prime of negative square root of 3 halves is also equal to 12, which means these are both concave up. And so these are our relative minimums. And so our minimum distance point, so our the 2 points, negative square root of 3 halves, comma. Now our original function, remember, was 4 minus x squared. So this is 4. Now when I square it, the negative doesn't matter, so I'll get 4 minus 3 halves, which is equal to the point negative 3 halves and 8 halves, 5 halves. Okay, so that point and negative, plus 3 halves, square root of 3 halves and 5 halves are the closest points. And the distance, well, that's the uppercase distance. That was the distance squared. Our distance is the square root of 0 minus the square root of 3, square root of 3 over 2 squared plus 2 minus 5 halves squared. So that's equal to the square root of, I get 3 halves plus, what is that? 3 halves squared then? That's 4 halves, oh no, minus 1 half squared, so plus 1/4. So this is the square root of 7/4, or the square root of 7 over 2 is the distance. Okay. So if we go back and look at this picture, square root of 7 is, well, let's see. So our point was the let me put in those points. Let's put in the point minus the square root of 3/2 and comma, and what was the y value? 5/2. 5/2. Okay, so there's that point, and then I can, if I copy that with a Control-C and use a Control-V to paste it, and then get rid of the negative. So there are my 2 points, and that is supposed to be a distance of square root of 7/2. So what the heck is square root of 7/2? Square root of 7, and then divided by 2, about 1.32, and sure, that looks reasonable because there's a distance of 1, so it'd be distance of 1 would be somewhere in there, and I could type the distance formula in, but I'll just kind of look at it and go, yeah, that looks right, about 1.32. And so there we go. That looks good. And now what I'd like to do is actually change our point from 0, 2. Let's move it over here to 1, 2. Okay. So we're gonna change to the point 1, 2. Now, what does that change? Well, our distance squared now of x is going to be 1 minus x squared plus 2 minus the what was it, 4x squared minus 2. Wait a minute, what the heck was y? I gotta go back here and find it. 4 minus x squared. I knew something just didn't look right. Okay, so sorry about that. Okay, 4 minus x squared. All right, so this is 1 minus x quantity squared plus, again, we get x squared, whatever that was, minus 2 squared. Once again, I can take the derivative using the chain rule, d prime of x, and we get 2 times 1 minus x times a negative 1 because of the chain rule, plus our 2 times x squared minus 2, and then times 2x. And let's see, so in this case, I think I'm probably better off just multiplying through by things, and so I've got a negative 2 times 1 minus x, so that'll be a 2x and minus 2, and then plus I've got my 4x times all this stuff, so I'll get a plus 4x cubed and minus 8x. And so this is 4x cubed minus 6x minus 2. So now I'll set that equal to 0. and solve that. And that is a bit harder, right? All of a sudden. I don't know. Can I, is there any way to, I can simplify it a little bit by dividing by 2. So 2x cubed minus 3x minus 1 equals 0. But now you see, as I look at that, I don't see something to group it. I don't see something to factor it really easily, and so I need to solve that equation. And in order to do that, so I've got 2x cubed minus 2x minus 1. So I can go here back to this whole thing. I'm going to put in the 1 here. I'm going to get rid of these. And now I'm going to put in a g of x equal 2x cubed minus 2x minus 1. And so now I see that actually only has 1 0. And as I look at the point, I feel like there should only be one point that's really close. And the 0 here is 1.191. Now, what is it? Well, it's a cube root of something or other. It'd be kind of interesting to see, I guess. I can play with things and say something like, what is 1.1? Wait a minute. 1.191, yeah, cubed, and I get 1.68. Now that doesn't help me at all, right? So I don't know what this is. It would be nice in some ways to get a closed form answer instead of a decimal approximation. Now here I can hit this fraction thing, but you see that didn't help either. I mean, I could tell you that was 1191 over 1,000. So I'll turn that off. And so what else could I do? Well, this is where Sage Cell can come in handy. If I go in here and I say var x, so I've just defined x as a symbolic variable. Now I can do something like s for solution is equal to and I'm going to try just saying solve, and my equation that I want to solve is again what was that, 2x cubed? Yeah, 2x cubed minus 2x. So 2, now here I have to actually do the asterisk and all that stuff. 2x cubed minus 2 times x minus 1 equals 0, and I want to solve that for x. And then I'm going to show that answer. And let's see if I got that right. Let's see. So again, 2x cubed minus 2x minus 1. Yeah, and I hit evaluate. And okay, now here's x equals, and notice it has an I in there. I don't want that answer. That's an imaginary or complex root. Here's another complex root because I see an I in there. Hopefully this has nothing. There we go. So there's the answer. Wow. Okay. I think I'll go back to the decimal, right? But there is the answer to this thing as far as what x is. I think I'll stick with 1.191. Okay, but I could, using this nice solver, get this nifty answer here. An interesting thing, right, is that what I have is the square root of 33 over 36 plus a fourth. And down here I have that same thing, the cube root of that. And down here I have that same thing, except it's 1 over 3 of those. Wow. Okay. So yeah, I wouldn't have gotten that. Possibly you all would have. Who knows? But I would not have gotten that. And so we'll just stick with our Desmos solution, 1.191, and so that is our x value, and so I can actually plot that point. I'll use 1.191 and f of 1.191 so that I can see that point. Well, that doesn't look right, does it? Okay, so my question is, I need to go back and check my math, I think. Okay, now how could we check the math? So I didn't plan on getting this wrong, but I think it's fine. I get things wrong. You probably will get things wrong at times. How do you know? Because here I think the point ought to be more like in here. Okay, so I think I did something wrong, and now I can do some fancy stuff here in Desmos. I can say, well, let's take h of x equal, and I'm going to set it to be our distance squared function. So x was 1, and then minus x, quantity squared, and then plus f of x, right? Or well, actually it's 2 minus f of x, quantity squared. Okay, so there's the function, and it looks to have that for an answer, 1.366. Okay, so if I plot that, 1.366 comma f of 1.366, that looks like a much better answer. Okay, so that looks to be correct. It should be 1.366. Okay, so where did I go wrong? You all didn't yell at me when I was doing my derivatives. Let's go check. It appears that's not the right derivative. Okay, so let's check math. And this is a nice thing about using technology and checking answers that way, if you can. And so I want to go back and check my calculations. So here I am pretty sure I got that part right. Let's look back up here just to kind of see what I did before. Okay, I had a 0 minus x quantity squared and a 2 minus 4 minus x squared, and I looked at this and had what, x squared minus 2 did I have x squared minus 2 down here? No, I had x squared minus 6 or something. No. Okay, change the point here. I had x squared minus 2. Whew. Okay, so that all looks good. Then I bring down the 2 times 1 minus x times the derivative of what's inside is minus x. And then here, I brought down the 2 times x squared minus 2 times 2x. Okay. So now, I have a negative 1 times 2 is negative 2 times 1. There's the negative 2. There's the plus 2x. And then here, I have 2 times 2 is 4x cubed, and then 2 times minus 2, that's a negative 4, and then times the 2x is negative 8x. So that, I believe, and oh, there we go. Gosh, it took me forever, but hey, 6 divided by 2 is 3, not 2. Okay, so you were probably yelling at me in the video that I got that wrong. So that should have been a 3x. And when we solve that, now with Desmos, I just go back here, I change that to a 3, and hopefully everything will line up. Get rid of that. And I need to find when that's 0, and that is 0 at 1.366. And so there you go. I should have had 1.366 here, and then it turns into the same thing I had down there. 366 and 366. So looks much better. So that's my point where I have a 0, and here I can see that it appears, that I'm going to have that there's a 0. I plotted the derivative and here, and I plotted my actual function I was minimizing here in blue. So let me make that disappear. So at this point, right, this is the information that I have, 1.366. And if I go back and take a second derivative, we know that, yeah, that's going to be the right answer. But actually, I have some other critical numbers. I have minus 0.366, and I have minus 1. So that's interesting, right? So if I'm here around minus 1, up there somewhere, you see I'm that far away, and so there is a local maximum, as well as when I'm here, I guess I have a local maximum. So somewhere in here. And so that's interesting, right? Is that I actually have 3 critical numbers, but doing it numerically here, so I plotted that. Now, go back here, and let's make that a 3 and evaluate. And yeah, see, now I do have three critical numbers. And, and oh, these are really nice critical numbers now, right? So here I've got some very nice numbers. And so this is getting long on this one, but I think it is worth it. And so I'm going to, while I'm looking here and talking about this, I'm going to write down the three numbers on my pad. So I have, the first one is 1/2 minus 1/2 times the square root of 3. I have another one that is the conjugate of that, not the complex conjugate, but just a plus that, and then -1. Okay, so I go back here. There are my three critical numbers. I know that the 1/2 plus square root of 3, or 1/2 the square root of 3, is the right answer. But let's take the second derivative, d double prime of x, and we get 6x squared minus 3. And so now, certainly if I look at d double prime of 1, -1, I get 6 minus 3, which is, really? 6 minus 3. Is that my, let's see, well, it should actually be 2 times that, because there's my actual derivative. But oh, that does make a difference. Yes, gotta work with the real derivative. Okay, so caught that quickly. My is 12x squared minus 6, and well, it did just I guess just double it, didn't it? 12x squared minus 6. Yeah, so that becomes, putting -1 in there, that becomes 12 minus 6, which is 6. Wow, I'm really messing this one up, because what's that say? That says concave up. Well, that would be a minimum. That's not a minimum. Okay, did I fix everything I was supposed to fix? I believe I did. Let's go back to Desmos. Okay, here I solved that. Here's Desmos. So you see, I can get confused and kind of wonder what's going on here too. So actually, is that right? So looking at the first derivative test, this is, I guess, concave up. Huh. Yeah, look at that. I hadn't really thought about that. I was thinking those would both be relative maximums. But they're, no, look at the first derivative test. It is indeed concave up. That's the tough thing. After you make one mistake, it's easy to think you've made more. But no, I did not make a mistake on this. That is concave up. That is a relative min. Oh, okay, so that's a possibility. All right, there's a relative min. And then d double prime of 1/2 minus 1/2 the square root of 3. Yuck, I've got to square that thing. So that's 12 times 1/2 minus the 1/2 square root of 3 squared minus 6. Now, what I do see is that when I square that, I will get what, 12 times, I'll get a fourth from that square. I'll get, when I multiply the two terms together, I'll get a minus 1/4, but two of them, so 1/2 square root of 3, and then plus 3 over 4, so 3/4, and minus 6. So that's equal to that and that make 1, and so I'll get 12 minus 6, which is 6, and minus 6 times the square root of 3. And 6 times the square root of 3 is bigger than 6, so this is negative, less than 0. And so that's a relative max at that point. And then d double prime of 1/2 plus 1/2 square root of 3 is equal to our 12 times 1/2 plus 1/2 square root of 3 squared minus 6. Well, we get almost the same thing we did before. We will get our 12 times 1/4, but then plus 1/2 square root of 3 and plus 3/4 minus 6. So that ends up being 6 plus 6 times the square root of 3, and that's greater than 0, another relative min. So now you see, if we didn't have our picture where we already know the answer, I would need to check our function value at both -1 and at 1/2 plus square root of 3 over 2. And so, you know, I need our d of -1 and d of -1. Again, oops, gotta go find d. Here is d. All right, so that's our 1 minus a -1 squared plus our 2 minus 4 minus -1 quantity squared there, and so that's 2 squared plus 4 minus 1 is 3, 2 minus 3 is -1, and so I'll get -1 squared, and so I get 5 for that distance squared. So that's looking like a big number, right? And then our d of 1/2 plus 1/2 square root of 3. You know, that looks terrible to have to deal with, right? 1 minus 1/2 minus 1/2 square root of 3 squared, and then plus, and again, this is just x squared minus 2, so I'm going to write it that way. 1/2, oops, I put up minus, that should be a plus. 1/2 plus 1/2 square root of 3 squared minus 2 all squared. Wow, this is just nasty as all get out, isn't it? I usually don't subject you to this kind of crap. I mean, you know, this just gets old really fast. But nothing wrong with a little old school here sometimes, just to see, yeah, you know, technology makes my life a lot easier in so many ways. But so here I'll get 1/2 minus 1/2 square root of 3 squared. And in here, oh, I've got to square that whole thing out. Here first. Yeah. Okay, so I get the 1/4 plus 1/2 square root of 3 plus 3/4, and then that's minus 2 all squared. So that's the 1/2 minus square root of 3 over 2 squared. And here I get the 1/4, 3/4, so that's 1 minus 2. So this one is the square root of 3 over 2 minus 1 squared. Wow. Okay, so that's 1/4 minus the square root of 3 over 2 plus 3/4, and then plus what, 3 over 4 minus the square root of 3, and then plus 1. Wow. Okay, so this is equal to, I got 1 here, 1 there, that's 2, 2 3/4, so that's 8 11/4, plus, nope, minus, sorry, minus 1.5, it looks like, so 3 square root of 3 over 2. And so, well, 3 square root of 3 is like 1.7, so this is around 5/2 here, and this is right, is that 5/2? Yeah, about 2.5. This is 2 3/4. You know, so this is a much smaller number. Again, well, I guess I'd need to go to a calculator to check it, but I can tell this is less than this 5 back here. So after all that, yeah, x is equal to 1/2 plus the square root of 3 over 2, and my distance squared is this thing that I got. So my distance is, I guess, the square root of 11 over 4 minus 3 square root of 3 over 2. Wow. That was a lot more than I thought I would be doing. But if you hung in there, you know, I think it's good to see these problems can get very messy, and that is where using technology can be helpful. And maybe I'll do this totally with Sage just to kind of show we can cut through a lot of this nasty stuff using technology, but still get full answers. Okay, so we will call this video done.